So before we begin solving this problem, we need to know that we hear beat when we'll have difference in frequencies. Now here we have two violin strings that are tuned to the same frequency at 294 hertz. So we won't hear any beats. But when the tension in one string is decreased, then we'll have some difference in frequencies, and only then we'll have the beat frequency. So to begin, if we look at the hint, so equation 11.13 gives us this equation right here. So this is an equation where you can find your velocity if you know the tension and mass per unit length of the chord. So for our case, the chord is string. So if we so yeah, if we have to find the frequency um, from section 12.4, we see that the frequency for violin string is given by f equals the speed of sound over twice the length. And if we substitute this velocity from this expression, we get something like this, where we don't know the tension and mass per unit length, but we don't need it because we have a hint which is given here. It says our tension in the string is decreased by 0.25%. So we know that this frequency is 294 hertz. Now if the tension in the string is decreased by 2.5%, then our velocity will change, and that will change our frequency as well. So the new frequency will be f prime, which is equal to 1 over twice of L. And then, so if it's decreasing by 2.5%, that means it's 0.975 of the tension, of the initial tension, and then we have the mass density or mass per unit length. Now if we plug in, if we take this guy out, we get square root of 0.925, sorry, it's gonna be square root of 0.975, that times the fundamental frequency that we had, right? So that's how we know that we have a difference in frequencies. So the beat frequency will be f, which is f minus f prime. Now that's gonna be f 1 minus square root of 0.975, and if we solve for it, we know f, which is 294 hertz. So that 75, that will give us our beat frequency, which is 3.7 hertz. Thank you.